Tonight, we're going to explore a question physicists have argued about for over a century. Have we finally found a real wormhole? Not in a movie, not in a novel, in actual data, gathered by actual telescopes, pointed at actual objects sitting light years from Earth. For decades, wormholes existed purely as a mathematical curiosity, a strange solution to Einstein's equations that most physicists assumed could never actually exist in nature. Recently, that assumption has been quietly challenged by a series of unusual observations that some researchers believe might be the first real evidence of a tunnel through the fabric of space itself. By the end of tonight, you're going to understand exactly what a wormhole actually is, what scientists think they may have found, and why the answer remains one of the most contested questions in modern physics. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. So let's begin. To understand what a wormhole actually is, you first have to understand what space itself actually is, according to Einstein. Before Einstein, most physicists imagined space as a fixed, unchanging backdrop, a rigid stage on which the universe simply played out its events. Einstein's general theory of relativity, published in 1915, replaced that rigid stage with something far stranger. Space, according to Einstein, is not fixed at all. It bends, it stretches, it curves in response to mass and energy, the same way a heavy ball placed on a stretched rubber sheet creates a dip that pulls smaller objects toward it. This bending of space is what we experience as gravity. Planets do not orbit the sun because some invisible force reaches out and pulls them. They orbit because the sun's mass curves the space around it, and the planets are simply following the straightest possible path through that curved space. This single idea, that space itself can bend, opened the door to something far stranger than ordinary gravity. If space can curve gently, under the influence of an object like the sun, what happens if it curves so extremely that it folds back on itself? Let's follow that question, because it leads directly to the mathematics of the wormhole. In 1935, Albert Einstein and physicist Nathan Rosen were studying the equations describing black holes when they noticed something unusual. The mathematics describing the extreme curvature around a black hole seemed to allow for a second solution, a kind of mirror image, connected to the first through a narrow throat of curved space. In other words, the equations suggested that two separate regions of space, potentially separated by enormous distances, or even existing in entirely different universes, could be connected by a kind of tunnel. This tunnel came to be known as an Einstein-Rosen bridge, and it is the direct mathematical ancestor of what we now call a wormhole. Let's be clear about something important before we go further. Finding a solution in the mathematics of general relativity does not automatically mean that solution exists in the real universe. Einstein and Rosen themselves were skeptical that their bridge could ever form naturally, or that anything could actually survive passing through it. Later calculations, performed by physicist John Wheeler and others in the 1950s and 60s, only deepened that skepticism, showing that the simplest version of an Einstein-Rosen bridge would collapse and pinch shut almost instantly, far too quickly for anything, even a beam of light, to cross from one side to the other. For decades, this seemed to settle the matter. Wormholes were a mathematical curiosity, an interesting solution to Einstein's equations, but not something that could plausibly exist as a stable, traversable structure anywhere in the real universe. Let's talk about what changed that assumption, because the story does not end there. In 1988, physicists Kip Thorne and Michael Morris, working at Caltech, revisited the wormhole problem with a very specific and unusual motivation. A science fiction author, working on a novel that would eventually become the basis for the movie Contact, had asked Thorne for a scientifically plausible way to send a character across vast interstellar distances without violating the laws of physics. Thorne and Morris discovered that a wormhole could, in principle, remain open and stable, but only if it were held open by an exotic form of matter, one with negative energy density, a property unlike anything ordinary matter possesses. This kind of exotic matter is not simply hypothetical in the way a fictional substance would be. Negative energy densities have actually been observed in laboratory experiments, in a phenomenon called the Casimir effect, where two closely spaced metal plates in a vacuum experience a measurable force caused by fluctuations in the quantum vacuum between them. The amounts of negative energy produced by the Casimir effect are astonishingly small, nowhere close to what would be needed to hold open a wormhole large enough for anything meaningful to pass through. But its existence proved that negative energy is not purely fictional. It is a real, measurable, if extremely limited, feature of our universe. Let's think about what this means for the broader question of whether wormholes could actually exist. Thorne and Morris's work transformed wormholes from a mathematical dead end into a genuine, if extraordinarily difficult, theoretical possibility. If enough exotic matter with negative energy density could somehow be gathered and arranged correctly, the mathematics suggests a wormhole could, in principle, remain open long enough for something to pass through it. The obstacle is not that the physics forbids it entirely. The obstacle is that the amount of exotic matter required appears to be so enormous, so far beyond anything currently achievable, or even remotely close to naturally occurring in the universe, that most physicists still consider a human-made or naturally forming traversable wormhole essentially impossible with our current understanding of physics. And yet, this is precisely the point where recent astronomical observations enter the story. Let's talk about what those observations actually are, because this is where things get genuinely interesting. Over the past several years, astronomers studying certain distant, extremely compact objects have noticed behavior that does not fit neatly into the standard picture of a black hole. Black holes are defined by an event horizon, a boundary beyond which nothing, not even light, can escape. Everything that falls past that boundary is, according to standard theory, gone forever, crushed toward a singularity at the center, where our current understanding of physics simply breaks down. Some researchers have proposed that certain exotic compact objects, indistinguishable from black holes using most conventional observations, might actually lack a true event horizon, and might instead have some kind of surface, or throat, through which infalling matter could, in principle, reappear elsewhere. If such an object existed, it would look almost identical to an ordinary black hole from a distance, bending light, pulling in nearby matter, producing the same general gravitational effects. But its behavior in certain extreme, specific circumstances might differ in small, measurable ways. Let's talk about the specific signal researchers have been looking for, because it centers on gravitational waves. When two extremely dense objects, such as black holes or neutron stars, spiral into each other and merge, they release a burst of gravitational waves, ripples in the fabric of space-time itself, detectable by instruments like the LIGO and Virgo observatories here on Earth. If two ordinary black holes merge, the resulting gravitational wave signal follows a well-understood pattern. A rising frequency as the two objects spiral closer together, followed by a sudden cutoff as they merge, and the newly formed, larger black hole settles into its final, stable shape. Some physicists have proposed that if one or both of the merging objects were not a true black hole, but instead a horizonless object, sometimes described theoretically as related to a wormhole structure, the gravitational wave signal might not cut off cleanly after the merger. Instead, faint, repeating echoes might appear in the data afterward, caused by gravitational waves reflecting off the object's unusual internal structure, rather than being fully absorbed as they would be by a true event horizon. Let's talk about whether these echoes have actually been detected. because this is the heart of the entire question. Since LIGO's first confirmed detection of gravitational waves from a black hole merger in 2015, several independent research teams have combed through the resulting data, specifically searching for these predicted echo signals. The results have been genuinely mixed and remain a significant point of active scientific disagreement. Some early analyses reported tentative statistical evidence for echo-like signals in a handful of detected mergers, generating considerable excitement within certain corners of the physics community. Other research teams, reanalyzing the exact same data using different statistical methods, found no significant evidence for these echoes at all, concluding that the earlier apparent signals were most likely the result of ordinary detector noise, misinterpreted as a meaningful pattern. This kind of disagreement is common in cutting-edge physics, particularly when searching for extremely faint signals buried within noisy data. And it means that, as of today, no gravitational wave echo has been confirmed with the level of statistical certainty required for the broader scientific community to accept it as genuine evidence of a horizonless, wormhole-like object. Let's talk about another category of observation that has generated recent excitement, involving the behavior of light around certain supermassive black holes. Wormholes, according to the mathematics developed by Thorne, Morris, and later researchers, would bend light in ways subtly different from an ordinary black hole, particularly in how they would produce what is called a photon ring, a thin, bright circle of light formed by photons that have orbited the object multiple times before escaping toward a distant observer. In 2019, the Event Horizon Telescope collaboration produced the first ever direct image of a black hole's shadow, capturing the supermassive black hole at the center of the galaxy M87. Since then, researchers have proposed that sufficiently precise future observations of similar photon rings, particularly around the black hole at the center of our own galaxy, Sagittarius A star, might reveal subtle differences distinguishing a true black hole from a hypothetical wormhole mouth. Current observations, while extraordinary achievements in their own right, do not yet have the resolution required to distinguish between these two possibilities with confidence. The predicted differences are extremely subtle, and separating them from ordinary black hole behavior would require levels of precision beyond what current telescope arrays, even ambitious ones like the Event Horizon Telescope, can currently achieve. Let's talk about a separate line of theoretical research that connects wormholes to an entirely different area of physics, one that has generated considerable interest in recent years. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a striking conjecture, sometimes summarized by the shorthand ER equals EPRA, linking Einstein-Rosen bridges directly to a completely different and seemingly unrelated concept called quantum entanglement. Quantum entanglement describes a strange phenomenon in which two particles become linked in such a way that measuring the state of one instantly correlates with the state of the other, regardless of the distance separating them, a phenomenon Einstein himself famously distrusted, describing it as spooky action at a distance. Maldacena and Suskind's conjecture suggests that entangled particles might, in some deep, still poorly understood mathematical sense, be connected by microscopic wormholes, tiny Einstein-Rosen bridges, linking them together even across vast distances. This idea remains highly theoretical, existing primarily within advanced mathematical physics, rather than as something directly observable with current instruments. But it represents a genuinely serious effort by leading physicists to connect wormholes, once dismissed as an exotic mathematical curiosity, to one of the most well-established and thoroughly tested phenomena in all of quantum physics. If the conjecture eventually proves correct, it would suggest that wormholes, in some microscopic sense, might be far more common throughout the universe than anyone previously imagined, existing invisibly within the quantum entanglement, connecting countless particle pairs, even if none of them are anywhere close to large enough for anything, or anyone, to actually pass through. Let's return to the specific astronomical claims that prompted tonight's exploration. because it is worth examining exactly how strong or weak the current evidence actually is. Several popular science articles and social media discussions in recent years have referenced specific supermassive black hole candidates, suggesting their observed behavior might be better explained by a wormhole model than by a standard black hole model. In most of these cases, the underlying scientific papers are considerably more cautious than the popular coverage surrounding them, typically presenting a wormhole interpretation as one mathematically consistent possibility among several, rather than as a confirmed or even strongly favored explanation. Standard black hole models continue to explain the vast majority of observed data extremely well, and the scientific principle of parsimony, favoring the simplest explanation consistent with the evidence, continues to favor conventional black holes over the far more exotic and mathematically demanding wormhole alternative in essentially every case examined so far. This does not mean the wormhole hypothesis is being dismissed unfairly. It means that, given the enormous theoretical requirements involved, particularly the need for exotic negative energy density in quantities never observed anywhere in nature, extraordinary evidence would be required before the physics community broadly accepted a wormhole interpretation over the much simpler black hole explanation. Let's talk about what it would actually take to confirm the existence of a real wormhole, since this helps clarify why the question remains so difficult to answer definitively. Ideally, scientists would want to observe something passing into one side of a suspected wormhole and reappearing, in a causally connected and verifiable way, on the other side, a level of direct confirmation currently far beyond any existing technology, and likely to remain so for the foreseeable future, given the vast distances and exotic conditions involved. Short of that, the strongest indirect evidence would come from a clear, statistically robust, and independently replicated detection of gravitational wave echoes following a black hole merger. Since this remains one of the few observational signatures, current theoretical models predict specifically for horizonless, wormhole-like objects, rather than ordinary black holes. As gravitational wave detectors continue to improve in sensitivity, and as more merger events are recorded and analyzed, the statistical power available to either confirm or definitively rule out these echo signals will continue to grow, potentially settling this particular question within the coming decade, one way or the other. Let's step back and consider the broader significance of this ongoing search, regardless of how it eventually resolves. Wormholes occupy a rare and interesting position in modern physics, a concept that emerges directly and legitimately from our best current understanding of gravity, yet one that appears, based on everything we currently know about matter and energy, to be forbiddingly difficult, or perhaps entirely impossible, to actually construct or encounter naturally. Studying wormholes, even purely theoretically, forces physicists to grapple with some of the deepest and most unresolved questions in the field. The true nature of negative energy, the ultimate fate of information that falls into a black hole, and the strange, still poorly understood relationship between gravity and quantum mechanics that theories like the ER=EPRA conjecture are attempting to address. Whether or not a real, traversable wormhole is ever confirmed to exist, the search itself continues to push the boundaries of what physicists understand about the fundamental structure of space, time, and the strange. Flexible fabric that Einstein first revealed to be far stranger than anyone before him had ever imagined. Let's talk about the specific object that has drawn the most attention in recent wormhole speculation. A supermassive black hole candidate that some researchers have suggested displays unusual characteristics worth further study. Sagittarius A star, the supermassive black hole at the very center of our own Milky Way galaxy, has been observed for decades through the careful tracking of stars orbiting extremely close to it, their precise, predictable orbital paths providing strong evidence for an enormously massive, compact object at the galactic center. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star's shadow, following their earlier historic image of the black hole in M87. providing scientists with an unprecedented, direct look at the immediate environment surrounding our galaxy's central supermassive object. Some researchers have proposed that future, higher-resolution observations of Sagittarius A star, potentially achievable through planned upgrades to the Event Horizon Telescope network, might finally have the precision required to detect the subtle differences a wormhole throat could theoretically produce in its surrounding photon ring, compared to the photon ring expected around an ordinary black hole. No such distinguishing evidence has been found yet, and most physicists working directly on these observations remain fully confident that Sagittarius A star is in fact an ordinary, if extraordinarily massive, black hole, consistent with everything general relativity predicts for such an object. But the mere fact that increasingly precise observations are approaching the theoretical threshold where a genuine distinction could eventually be drawn represents real, measurable scientific progress, regardless of which answer ultimately proves correct. Let's consider, finally, why this question captures public imagination so strongly, beyond its purely scientific significance. Wormholes occupy a unique place in popular culture, appearing throughout science fiction as a convenient shortcut across the vast, otherwise insurmountable distances separating stars and galaxies. A narrative device allowing characters to travel light years in moments rather than centuries. This cultural familiarity creates a natural, powerful curiosity whenever real scientific research even tangentially touches on the subject, often leading to significant gaps between the cautious, heavily qualified language used in actual physics papers and the much bolder, more exciting headlines used to describe that same research in popular media. Tonight's exploration has tried to walk carefully along that boundary, presenting the genuine, serious theoretical work being done on wormholes, the real, if still inconclusive, observational searches currently underway, and the honest, current scientific consensus, which remains that no confirmed evidence for a real, traversable wormhole yet exists anywhere in the universe. Let's zoom out one final time, because the story of the wormhole search is ultimately a story about the boundary between mathematical possibility and physical reality. Einstein's equations, written down over a century ago, contained within them a strange, almost hidden possibility, a tunnel through the fabric of space itself, connecting distant points or distant universes through nothing more than the extreme curvature of space-time. For most of the 20th century, that possibility remained a mathematical curiosity, interesting to specialists, but dismissed by nearly everyone as physically implausible, lacking any known mechanism that could actually bring such a structure into stable existence. Decades of careful theoretical work, from Einstein and Rosen through Thorne and Morris to Maldacena and Susskind, slowly transformed that dismissed curiosity into a legitimate, if still highly uncertain, subject of serious ongoing research, connected in increasingly deep ways to some of the most fundamental open questions in modern physics. And now, for the first time, astronomers possess instruments sensitive enough to actually search for observational evidence, gravitational wave echoes, subtle photon ring distortions, precise imaging of the shadows cast by the most extreme objects in the universe, capable of potentially answering, within our own lifetimes, a question that has existed purely as abstract mathematics for over 100 years. Have we finally found a real wormhole? As of tonight, the honest answer remains no, not yet, not with anything approaching the certainty science requires. But for the first time in the history of this idea, the question has moved from purely theoretical speculation into something astronomers can actually search for directly, in real data, gathered by real telescopes, pointed at the strangest, most extreme objects our universe has ever produced. Let's go back and look more closely at exactly what a black hole is, because understanding this deeply is the only way to appreciate why a wormhole would be so different and so much harder to prove. A black hole forms when an enormous amount of mass collapses into an extremely small volume, creating a gravitational field so intense that not even light, the the fastest thing in the universe, can escape once it crosses a specific boundary called the event horizon. Everything we currently understand about black holes comes from Einstein's general relativity, combined with decades of increasingly precise astronomical observation. From the earliest indirect detections through X-ray emissions in binary star systems to the direct imaging achieved by the Event Horizon Telescope in recent years. Inside the event horizon, according to standard theory, space-time becomes so extremely curved that all paths, no matter which direction an object tries to travel, lead inexorably toward a single point called the singularity, where the known laws of physics simply stop giving meaningful answers. This is one of the most unsettling aspects of black hole physics. The equations do not describe a strange, exotic place you could visit and survive. They describe the literal end of predictable physics, a boundary where our best theories admit their own limitations rather than making a false claim about being wrong. Let's think about how a wormhole would need to be fundamentally different from this picture in order to allow something to pass through and emerge somewhere else. Instead of leading toward a singularity, the space inside a wormhole's throat would need to somehow reconnect, opening back outward into a second region of space, rather than collapsing inward toward a point of infinite density. This requirement alone is what makes wormholes so mathematically demanding. Ordinary matter and energy, of the kind we observe throughout the universe, only ever curve space in ways that pull things together, focusing paths inward rather than allowing them to reconnect and open back outward. To hold a wormhole's throat open, physicists have calculated that you would need a source of gravitational repulsion, something that pushes space apart rather than pulling it together. Exactly opposite to how ordinary mass and energy behave. This is where the concept of negative energy density becomes essential, and also where the theoretical difficulty becomes almost overwhelming. Let's slow down on negative energy, because it is one of the most misunderstood concepts in this entire subject. Negative energy does not mean simply having less energy than zero in some ordinary sense, the way a bank account can go into debt. It refers to a specific measurable property within quantum field theory, where certain configurations of the quantum vacuum can have an energy density lower than what we normally consider the baseline vacuum state, effectively behaving as if that region of space contains less than nothing. The Casimir effect, mentioned earlier, is the clearest experimental demonstration of this strange property, produced when two uncharged metal plates are placed extremely close together in a vacuum. Quantum fluctuations that would normally exist freely in empty space become restricted between the plates, since only certain wavelengths can fit in the narrow gap, and this restriction creates a measurable negative energy density between them, pulling the plates together with a tiny but detectable force. Scientists have measured this effect in laboratories with remarkable precision, and it stands as solid, repeatedly confirmed proof that negative energy density is a real, physical phenomenon, not merely a theoretical trick invented to make wormhole equations work. Let's talk about the scale problem, because this is where the wormhole concept runs into its most serious practical obstacle. The amount of negative energy produced by the Casimir effect between two laboratory-sized plates is astonishingly tiny, many orders of magnitude smaller than what calculations suggest would be needed to hold open even a microscopic wormhole, let alone one large enough for a spacecraft or a human being to pass through. Some theoretical physicists have proposed exotic scenarios involving cosmic strings, hypothetical ultra-thin, ultra-dense structures theorized to have formed during the earliest fractions of a second after the Big Bang, as a possible natural source of sufficient negative energy density. No cosmic string has ever been directly observed, and their existence remains entirely speculative, meaning this proposed solution to the wormhole energy problem currently rests on one unconfirmed theoretical concept being used to support another. This layering of unconfirmed theoretical requirements, one hypothetical structure needed to explain how another hypothetical structure might work, is a significant part of why most physicists remain deeply skeptical that traversable wormholes exist anywhere in the natural universe, even while acknowledging that the underlying mathematics of general relativity does not, strictly speaking, forbid them outright. Let's turn now to a specific class of astronomical objects that researchers have suggested might, in principle, be distinguishable from ordinary black holes, given sufficiently advanced future observations. These objects are sometimes referred to broadly as exotic compact objects, a category that includes several distinct theoretical proposals beyond wormholes, such as boson stars, gravastars, and fuzzballs, each attempting to explain how an object with a black hole's extreme mass and compactness might avoid forming a true event horizon or singularity. Boson stars, for example, are theorized to be held together not by ordinary matter, but by a hypothetical class of particles that can occupy the same quantum state simultaneously, forming an extremely dense but horizonless object supported by quantum mechanical pressure rather than the crushing gravitational collapse that defines a black hole. Gravastars propose an even stranger structure, a thin shell of exotic matter surrounding a core of vacuum energy, mimicking a black hole's outward appearance almost perfectly, while avoiding the formation of an event horizon or singularity entirely. None of these alternative objects have been confirmed to exist, and all of them, including wormholes, remain firmly in the category of theoretical possibilities that current observations cannot yet definitively rule in or rule out, given the technological limitations of even our most advanced telescopes and detectors. Let's return to gravitational wave astronomy, because this remains the most promising observational avenue for distinguishing between these possibilities in the coming years. Since 2015, the LIGO and Virgo detectors have recorded dozens of confirmed black hole and neutron star mergers, each producing a distinctive gravitational wave signature that scientists can compare against theoretical predictions with increasing precision as detector sensitivity continues to improve. A newer generation of gravitational wave detectors, including planned space-based observatories like LISA, expected to become operational in the coming years, will be sensitive to a completely different range of gravitational wave frequencies than ground-based detectors like LIGO, potentially opening up entirely new categories of merger events to study, including mergers between much larger supermassive black holes at the centers of galaxies. If gravitational wave echoes, the specific signature theorized to indicate a horizonless object rather than a true black hole, exist in nature at all. This expanding network of increasingly sensitive detectors represents humanity's best current chance of eventually detecting them with enough statistical confidence to settle the debate. Let's think about the timeline involved here, since patience remains an unavoidable part of this particular scientific story. LISA is not expected to become fully operational until sometime in the 2030s, meaning any potential breakthrough relying on this next-generation instrument remains, at minimum, several years away, even under an optimistic development and launch timeline. Ground-based detectors continue operating and improving in the meantime, with each new observing run adding additional merger events to the growing catalog available for analysis, gradually increasing the statistical power available to either detect a genuine echo signal or definitively rule one out within the sensitivity range these existing detectors can currently achieve. Science of this kind rarely resolves quickly. It advances through a slow, cumulative process of gathering more data, refining analysis techniques, and gradually narrowing the range of remaining theoretical possibilities, exactly the kind of patient, incremental progress that has defined nearly every major astronomical discovery covered on this channel. Let's talk about how the Event Horizon Telescope actually works, because understanding its method helps explain both what it has already achieved and why distinguishing a wormhole from a black hole remains beyond its current reach. Rather than being a single telescope, the Event Horizon Telescope is a global network of radio observatories spread across multiple continents, from Antarctica to Hawaii to Spain, all pointed at the same target simultaneously. and combined using a technique called very long baseline interferometry. By linking observatories separated by distances comparable to the diameter of Earth itself, scientists can achieve an effective resolving power equivalent to a single telescope the size of our entire planet. Sufficient, just barely, to resolve the tiny apparent size of a black hole's shadow, even from thousands of light years away. Producing the historic image of the M87 black hole in 2019 required years of preparation, a coordinated observing campaign lasting only a matter of days, and then nearly 2 more years of painstaking data processing. Cross-checking results between independent teams working with the same raw data to ensure the final image was not simply an artifact of the complex reconstruction process. The resulting image, a fuzzy but unmistakable ring of light surrounding a dark central shadow, matched theoretical predictions for an ordinary black hole with remarkable precision, providing some of the strongest direct visual evidence, yet supporting general relativity's predictions in the most extreme gravitational environment ever directly observed. Let's think about what would need to improve for this same technique to eventually distinguish a wormhole from a black hole. Current models suggest that a wormhole's photon ring, the bright circle of light produced by photons orbiting the object multiple times before escaping toward Earth, might display subtle asymmetries or additional substructure not present around an ordinary black hole, caused by light potentially passing through the wormhole's throat and emerging on the other side before completing its journey to our telescopes. These predicted differences are exceptionally subtle, likely requiring resolving power several times greater than what the current Event Horizon Telescope Array can achieve. A level of improvement scientists hope to reach through planned expansions of the network, including additional observatories and, potentially, dedicated space-based radio telescopes that would extend the effective baseline far beyond the diameter of Earth itself. Proposals for exactly this kind of space-based expansion, sometimes discussed under names like the Event Horizon Explorer, remain in early planning stages, without a confirmed launch date, meaning any potential future ability to directly distinguish a wormhole photon ring signature from an ordinary black hole signature likely remains at least a decade away, dependent on funding, technical development, and successful international collaboration across multiple space agencies. Let's shift focus now to a slightly different, though closely related, theoretical proposal that has generated its own share of recent attention, involving the interior structure of black holes rather than their exterior appearance. Traditional black hole theory predicts a singularity at the very center, a point of infinite density where our equations break down entirely, unable to make any further meaningful prediction about what actually happens to matter that falls all the way to the center. Some physicists find this singularity deeply unsatisfying, not because it violates any specific observation, but because a genuine infinity appearing in a physical theory is often taken as a signal that the theory is incomplete, missing some deeper piece of physics that would resolve the infinity into something finite and physically sensible. One proposed resolution, called the fuzzball model, developed primarily within the context of string theory, suggests that what we call a black hole's interior is not an empty space surrounding a singular point at all, but rather an enormously complex, tangled structure made of extended, string-like objects, filling the entire volume that a classical black hole model would otherwise treat as empty space surrounding a central singularity. In this model, there is no singularity, no true event horizon in the traditional sense, and, crucially, information that falls into the black hole is not lost or destroyed, but rather encoded somewhere within this complex fuzzball structure, potentially resolving one of the most famous and persistent puzzles in theoretical physics, known as the black hole information paradox. Let's think about how this connects back to the wormhole question, since these ideas are more closely related than they might initially appear. Both the fuzzball model and the wormhole hypothesis represent attempts to resolve deep theoretical problems. The information paradox in one case, the nature of gravitational singularities in the other. By proposing that black holes are not quite what the simplest classical version of general relativity suggests they are. Neither model has been confirmed observationally, and both remain active, contested areas of theoretical research, illustrating just how much genuine uncertainty still surrounds our understanding of what actually happens in the most extreme gravitational environments the universe produces. This uncertainty is not a weakness in modern physics. It is, in a sense, exactly where physics is supposed to be at its current stage of development, actively working through unresolved tensions between general relativity, which describes gravity beautifully at large scales, and quantum mechanics, which describes the behavior of particles and fields beautifully at small scales, but which has never been fully and consistently unified with gravity in a single, complete theory. Let's return to the specific question of observational evidence one more time, because it is worth examining a few of the specific claims that have circulated in recent years with a more careful, skeptical eye. In several instances, researchers have pointed to unusual, unexplained variability in the light curves of certain distant, extremely compact objects, arguing that this variability might be more consistent with a wormhole's throat, allowing matter and radiation to pass through and interact with material on the other side, rather than simply falling permanently past an ordinary event horizon. In nearly every one of these cases, subsequent, more detailed analysis by independent research groups has found that the observed variability can be explained equally well, or often better, by more conventional astrophysical processes, such as irregular accretion disk behavior, gravitational lensing effects from unrelated foreground objects, or simple instrumental noise and calibration errors in the original data. This pattern, an initial exciting claim followed by more careful analysis revealing a more mundane explanation, is extremely common throughout the history of astronomy, and does not necessarily reflect poorly on the scientists who proposed the more exotic interpretation in the first place. Science, especially science pushing right up against the limits of what current instruments can measure, often requires proposing bold, testable hypotheses precisely so that the community can rigorously attempt to falsify them. A process that strengthens our overall understanding, regardless of whether any individual bold hypothesis ultimately turns out to be correct. Let's think about the role of skepticism in this entire field, because it plays an especially important part in extraordinary claims of this kind. The physicist and astronomer Carl Sagan famously argued that extraordinary claims require extraordinary evidence, a principle that applies with particular force to any claim suggesting the discovery of a wormhole, given how dramatically such a discovery would need to overturn or extend our current understanding of physics. A single unusual data point, or a single unexplained variability pattern, however intriguing, does not meet this bar, since numerous mundane explanations typically remain available and must be carefully ruled out before a more exotic interpretation can be seriously entertained by the broader scientific community. This is precisely why claims about potential wormhole detections tend to generate significant public excitement and media coverage, while receiving a far more cautious, qualified reception within the peer-reviewed scientific literature itself. A gap that often leads to public confusion about how close scientists actually believe we are to a genuine discovery. Let's talk about how this gap between popular coverage and scientific consensus tends to form, since understanding it helps make sense of why wormhole stories circulate so persistently online, despite the lack of confirmed evidence. A researcher might publish a paper exploring a mathematically consistent wormhole model that could, in principle, explain a particular set of observations, carefully noting throughout the paper that conventional black hole models remain equally or more consistent with the same data, and that further observation would be needed to distinguish between the possibilities. By the time this nuanced, heavily qualified research makes its way into a news article, and subsequently into social media summaries and video content built from that article, the careful qualifications are often stripped away entirely, leaving behind a much bolder, more attention-grabbing headline suggesting scientists may have found a real wormhole, a framing the original researchers themselves would likely consider a significant overstatement of their actual findings. This channel has tried, throughout tonight's exploration, to present the genuine, careful, heavily qualified state of current research, rather than repeating the more sensationalized versions of this story that circulate elsewhere. Because understanding the real, current limits of scientific knowledge is, in its own way, just as fascinating as the more dramatic claims that sometimes overshadow it. Let's go back even further into the history of this idea. Because the concept of connecting distant regions of space through some kind of shortcut did not begin with Einstein and Rosen in 1935. Even before general relativity existed, mathematicians studying curved geometric surfaces had already explored abstract spaces containing handles or tunnels connecting otherwise separate regions, purely as an exercise in topology, the branch of mathematics concerned with the properties of shapes that remain unchanged under stretching or bending. These early mathematical explorations had no direct connection to physics at the time, existing purely as elegant, abstract curiosities within pure mathematics. Decades before Einstein's theory of gravity gave physicists a reason to wonder whether such structures might actually correspond to something physically real. When Einstein and Rosen discovered their bridge solution in 1935, they were, in a sense, rediscovering a structure mathematicians had already been studying abstractly, but now finding it emerging naturally and unavoidably from the equations describing gravity itself, transforming a purely mathematical curiosity into a genuine question about the physical structure of the universe. Let's think about how the term wormhole itself came into use, since its origin offers a helpful, intuitive way to picture what these structures are supposed to represent. The physicist John Wheeler, who did extensive foundational work studying the stability and behavior of Einstein-Rosen bridges in the 1950s, is generally credited with coining the term wormhole, drawing an analogy to how a worm might tunnel directly through an apple, connecting 2 points on the apple's surface by a much shorter path than traveling all the way around the outside. This analogy captures the basic appeal of the wormhole concept perfectly. If ordinary space is like the surface of the apple, curved and requiring a long journey to travel between 2 distant points, a wormhole would function like the worm's tunnel, a shortcut passing through a higher dimensional structure, allowing a much shorter effective path between 2 points that would otherwise be separated by an enormous distance. Wheeler's own calculations, however, were among the first to demonstrate that the simplest version of this structure would be highly unstable, collapsing and pinching shut almost instantaneously, a finding that dampened serious scientific interest in wormholes for decades until Thorne and Morris revisited the problem in the 1980s with their exotic matter solution. Let's think about the broader philosophical and scientific significance of that decades-long gap between Wheeler's discouraging calculations and Thorne and Morris's later work showing a path forward. Science does not always progress in a straight line. An idea can be explored, found to face what appears to be a fatal obstacle, and then set aside for years, or even decades, only to be revisited later when new theoretical tools or a renewed, sometimes unusual motivation, such as a science fiction author's request for scientific plausibility, brings fresh attention and a new angle of attack to an old, seemingly settled problem. This pattern appears repeatedly throughout the history of physics, ideas dismissed prematurely, only to be rehabilitated later once the full complexity of the problem and the full range of possible solutions becomes better understood by a new generation of researchers approaching the question with fresh perspective and improved mathematical tools. Let's talk about how modern computational tools have changed the way physicists study wormhole solutions today. Compared to the purely analytical, pencil and paper methods available to Einstein, Rosen, and even Wheeler decades later, modern researchers studying wormhole stability and behavior increasingly rely on sophisticated numerical simulations, run on powerful computers, capable of modeling the complex, dynamic behavior of curved space-time in ways that would have been utterly impossible to calculate by hand using the analytical methods available in the middle of the 20th century. These simulations allow physicists to explore a much wider range of hypothetical exotic matter configurations, testing which specific arrangements, if any, might successfully hold a wormhole's throat open long enough to be theoretically traversable, and identifying more precisely which mathematical possibilities remain viable candidates worth further study. While this computational approach has significantly refined scientists' understanding of exactly what would be required to stabilize a wormhole, it has not fundamentally changed the basic conclusion reached decades earlier by Thorne and Morris, that the exotic matter requirements remain extraordinarily demanding, likely far beyond anything achievable using any physical process currently known to occur naturally anywhere in the universe. Let's consider an entirely different angle on this question, moving away from astrophysical observation and toward particle physics experiments conducted here on Earth. Some researchers have speculated that extremely high-energy particle collisions, of the kind produced inside instruments like the Large Hadron Collider, might, under certain highly theoretical and speculative models involving extra-spatial dimensions, briefly create microscopic wormholes existing for only an infinitesimally small fraction of a second before immediately evaporating. No evidence for any such microscopic wormhole formation has ever been observed at the Large Hadron Collider or at any other particle accelerator, and the theoretical models predicting this possibility generally require additional, currently unconfirmed physics, such as extra spatial dimensions beyond the three we experience directly. Assumptions that remain entirely speculative and unsupported by any current experimental evidence. This does not mean the idea is unscientific, since it does generate specific, testable predictions that experiments can search for. It simply means that, like so much else in this story, it remains firmly in the category of an interesting, mathematically consistent possibility that current evidence neither confirms nor definitively rules out, awaiting either future higher energy experiments or some other, currently unforeseen observational breakthrough to move the question meaningfully forward one way or the other. Let's think about what a confirmed wormhole discovery would actually mean for humanity, setting aside for a moment the significant remaining scientific uncertainty, purely as a thought experiment about its potential implications. If a genuinely stable, traversable wormhole were ever discovered, or somehow constructed, it would represent one of the most significant scientific and technological milestones in human history, potentially opening a pathway to interstellar travel that completely bypasses the otherwise insurmountable distances and travel times involved in crossing the vast, empty gulfs of space separating our solar system from even the nearest neighboring stars. Current technology, even our fastest spacecraft, would require tens of thousands of years to reach the nearest star system beyond our own sun, a timescale that makes conventional interstellar travel essentially impossible within any human lifetime, or even across many consecutive human generations. A functioning wormhole, connecting two distant points in space through a dramatically shorter effective path, could, in principle, reduce that journey to a fraction of the time, transforming interstellar travel from a purely theoretical, almost fantastical concept into something approaching genuine, practical feasibility. This enormous potential payoff is, in part, exactly why the search for real, physical evidence of wormholes continues to attract serious scientific attention, despite the extraordinarily demanding theoretical requirements and the current complete absence of confirmed observational evidence. Because the implications of eventually finding one would be transformative enough to justify continued, careful, rigorous investigation. Let's think through the practical mechanics of what actually traveling through a hypothetical stable wormhole might involve, according to the mathematics developed by Thorne and Morris. Their original model envisioned two spherical mouths, each existing at a different location in space, connected by a throat of exotic matter holding the structure open, with the geometry arranged so that an object entering one mouth would emerge from the other essentially instantaneously, or after only a brief, short duration, from the perspective of someone traveling through it. Crucially, the model requires the throat to remain wide enough, and the tidal forces, the difference in gravitational pull between different parts of an object passing through, to remain gentle enough that a human being or a spacecraft could survive the passage without being stretched apart. An effect popularly referred to as spaghettification when discussing the fate of anything falling into an ordinary black hole. This requirement for a survivable, gentle passage is actually one of the more demanding aspects of the Thorne-Morris model, since many other theoretical wormhole solutions, lacking carefully engineered exotic matter, would produce tidal forces strong enough to destroy anything attempting to pass through almost instantly, long before reaching the other side. Let's think about the energy requirements involved in maintaining such a structure over time, since even a theoretically stable wormhole would not necessarily remain that way indefinitely without ongoing intervention. Some calculations suggest that a wormhole held open by exotic matter might require continuous maintenance, additional exotic matter or energy input over time, to counteract natural instabilities that would otherwise cause the throat to gradually narrow and eventually collapse. Similar to how Wheeler's original, unstabilized bridge model collapsed almost immediately without any exotic matter present at all. This suggests that even in the most optimistic theoretical scenario where a wormhole could initially be created or discovered in a stable configuration, keeping it open and usable over any meaningful period of time might require an ongoing, potentially enormous commitment of exotic matter or energy, adding yet another layer of practical difficulty on top of the already extraordinary challenge of creating or locating such a structure in the first place. Let's consider for a moment the question of whether a naturally occurring wormhole, rather than an artificially constructed one, could plausibly exist anywhere in the universe without requiring any external engineering or maintenance at all. Some theoretical astrophysicists have proposed that conditions in the earliest moments after the Big Bang, when the universe was unimaginably hot, dense, and rapidly evolving, might have been extreme enough to naturally produce the necessary exotic matter configurations, potentially creating primordial wormholes that have persisted, in some stable or semi-stable form, ever since. This remains an extremely speculative proposal, difficult to test directly, since any such primordial wormhole would likely be microscopic in size, based on the physical scales involved in early universe cosmology, and would be exceptionally difficult to distinguish from other predicted exotic remnants of the early universe, such as primordial black holes, using any currently available observational technique. Nonetheless, this line of theoretical research illustrates how seriously some physicists take the possibility that wormholes, rather than requiring deliberate future engineering by an advanced civilization, might already exist naturally somewhere in the universe, formed by the extreme conditions of its own earliest, most chaotic moments, simply waiting to be discovered using sufficiently advanced observational methods not yet available to modern astronomy. Let's return one more time to the question of gravitational wave echoes, since new detector upgrades and expanded observation campaigns continue to refine the search with each passing year. The current generation of LIGO and Virgo detectors has undergone several rounds of sensitivity upgrades since the historic first detection in 2015, each upgrade allowing the observatories to detect fainter gravitational wave signals from more distant, and therefore more numerous merger events throughout the observable universe. A larger catalogue of confirmed mergers gives researchers searching for echo signals significantly more statistical power, since a genuine physical effect, if real, should appear consistently across many independent merger events, while a false positive caused by random detector noise would be expected to appear only sporadically, without a consistent, repeatable pattern across the growing dataset. Some of the most recent, large-scale statistical analyses, incorporating data from dozens of confirmed mergers, rather than just the handful available in the earliest years of gravitational wave astronomy, have found no statistically significant evidence for the predicted echo signal, placing increasingly strict upper limits on how strong, if it exists at all, any such effect could possibly be without having already been detected by current instruments. This growing body of null results does not definitively prove that horizonless, wormhole-like objects do not exist anywhere in the universe. It does, however, continue to narrow the range of theoretical models that remain consistent with observation, gradually eliminating some of the simpler, more optimistic wormhole and exotic compact object proposals that would have predicted a stronger, more easily detectable echo signal than what current data actually shows. Let's talk about a completely different kind of wormhole discussion, one that has emerged specifically from within the field of quantum computing, an area that might seem, at first glance, to have nothing at all to do with astrophysics or gravitational waves. In recent years, researchers using quantum computers have run experiments explicitly designed to simulate a simplified, highly idealized model of a wormhole, based directly on the theoretical framework connecting quantum entanglement to Einstein-Rosen bridges through the ER=EPRA conjecture discussed earlier. These experiments do not involve anything resembling an actual physical wormhole existing anywhere in real space. Instead, they use a quantum computer's qubits, the basic units of quantum information, to simulate the mathematical behavior predicted for a wormhole's information transfer properties, testing whether specially prepared quantum information behaves the way theoretical models predict it should if the ER=EPRA conjecture is correct. Some of these experiments, conducted using Google's Sycamore quantum processor and published in prominent scientific journals, reported results consistent with the predicted wormhole-like information transfer behavior, generating considerable media attention with headlines suggesting scientists had created a wormhole inside a quantum computer. Let's be extremely clear about what these experiments actually demonstrated, because the popular framing significantly overstated their actual scientific significance. No physical wormhole, no actual tunnel through space-time, existed anywhere during these experiments. The researchers simulated a simplified mathematical model, using quantum bits to represent abstract information rather than any physical spatial structure, testing a specific theoretical prediction about how entangled quantum systems should behave if the deep, still largely unproven mathematical connection between quantum entanglement and wormholes turns out to be correct. The experiment's actual scientific value lies in providing a controlled, repeatable way to test specific mathematical predictions of a highly abstract theoretical framework, offering physicists a useful new tool for probing extremely difficult, otherwise experimentally inaccessible questions about the relationship between quantum mechanics and gravity. Questions that remain among the most important unsolved problems in all of theoretical physics. Let's think about why this distinction matters so much, since confusing a mathematical simulation with an actual physical discovery represents exactly the kind of misunderstanding that fuels much of the exaggerated wormhole coverage circulating online. A simulation, however sophisticated, tests whether a mathematical model behaves the way theory predicts, under conditions carefully arranged by researchers specifically to isolate and test that particular prediction. An actual physical discovery would require observing a real, previously unexplained phenomenon occurring naturally in the universe, or successfully constructing a genuinely new physical structure using real matter and energy, neither of which describes what quantum computing experiments studying the ER=EPRA conjecture have actually accomplished, despite how their results are sometimes described in more sensationalized media coverage. This does not diminish the genuine scientific value of this research. It simply means understanding precisely what was tested, and what conclusion can and cannot be responsibly drawn from the results remains essential to accurately understanding where this area of physics genuinely stands today, separate from the more exaggerated claims that sometimes circulate around it. Let's shift our attention to a related, equally fascinating theoretical question, involving whether wormholes, if they existed, could theoretically allow travel backward in time, not merely across vast distances in space. Some solutions to Einstein's equations involving wormholes suggest that, under certain specific and highly exotic configurations, moving one mouth of a wormhole at high speed relative to the other, exploiting the time dilation effects predicted by special relativity, could create a difference in the flow of time between the two mouths, potentially allowing an object entering one side to emerge from the other side at a point earlier in time than when it entered. This possibility, first explored in detail by physicist Kip Thorne and his collaborators in the late 1980s, generated significant excitement and equally significant concern within the physics community, since time travel of this kind raises deeply troubling logical paradoxes, most famously illustrated by the so-called grandfather paradox, in which a time traveler could, in principle, prevent their own existence by interfering with events in their own past. In response to these concerns, physicist Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics, likely involving currently poorly understood quantum effects, would naturally prevent any such time travel paradox from ever actually occurring, effectively protecting the universe's timeline from being broken by exotic structures like time-traveling wormholes. Let's think about the current status of this debate, since it remains genuinely unresolved within theoretical physics. Hawking's chronology protection conjecture has never been proven or disproven with mathematical certainty, remaining, much like the wormhole concept itself, a serious, actively studied theoretical proposal rather than a settled scientific conclusion. Some researchers continue to explore mathematical models in which limited forms of time travel might be theoretically permitted without necessarily producing an unavoidable logical paradox, often relying on complex ideas involving self-consistent timelines, where any events occurring via time travel are automatically constrained to be consistent with the single, unified history that already occurred, effectively preventing paradoxes not by forbidding time travel entirely, but by restricting which specific time travel scenarios remain mathematically and physically permissible. This entire area of research remains firmly theoretical, disconnected from any current or foreseeable observational test, existing primarily as a fascinating illustration of how seriously physicists must grapple with the strange, sometimes deeply counterintuitive implications that emerge when Einstein's elegant equations are pushed to their most extreme mathematical limits. Let's bring the discussion back toward more immediately practical, astronomical research, since this remains the area most likely to produce genuine, testable progress in the coming years, compared to the far more speculative territory of time travel physics. Beyond gravitational wave echoes and photon ring imaging, researchers have also proposed searching for wormholes through their potential gravitational lensing signatures, the way light bends when passing near an extremely massive object, producing distorted or duplicated images of more distant background objects positioned directly behind it from our point of view. A wormhole mouth, according to some theoretical models, might produce a subtly different lensing pattern compared to an ordinary black hole or other massive compact object, particularly if light is able to pass directly through the wormhole's throat rather than simply bending around its exterior, potentially creating unusual, currently unobserved lensing signatures that sufficiently advanced future sky surveys might eventually be able to detect. Large-scale astronomical surveys currently underway, and additional next-generation surveys planned for the coming decade, are expected to catalogue gravitational lensing events in far greater numbers and with far greater precision than any previous survey, potentially providing enough data for researchers to systematically search for these unusual, wormhole-specific lensing signatures across a much larger sample of candidate objects than has ever been possible before. No such signature has been confirmed in any existing survey data, but the sheer increase in data volume and precision expected from upcoming astronomical surveys represents another genuine, concrete avenue through which real observational progress on this question could plausibly occur within the coming years, rather than remaining confined purely to theoretical speculation indefinitely. Let's talk about the specific scientists currently leading research in this field, because understanding who is doing this work and how they approach it helps clarify how seriously and how cautiously this research is actually being conducted. Physicist Pavel Bushev and colleagues, along with several other independent research groups scattered across universities in Europe, the United States, and Asia, continue to publish theoretical papers exploring increasingly refined models of what a realistic, observationally distinguishable wormhole signature might actually look like, carefully building on the foundational work established decades earlier by Thorne, Morris, Maldacena, and Susskind. Much of this ongoing work involves incremental refinement rather than dramatic breakthrough, researchers testing slightly different exotic matter configurations, slightly different assumptions about the relationship between a wormhole's mass and its throat size, and slightly different predictions for exactly what an echo signal or photon ring distortion should look like under each specific model, gradually building a more complete map of exactly what future observations would need to detect or fail to detect to meaningfully constrain these theoretical possibilities. This is what genuine scientific progress in a highly theoretical, currently unconfirmed field generally looks like from the inside. Less a single dramatic eureka moment, and more a slow, careful, collaborative process of proposing increasingly specific testable predictions, then patiently waiting for observational technology to catch up to the point where those predictions can actually be checked against real data. Let's think about how funding and career incentives shape this particular area of research, since this context helps explain why both the exciting and the skeptical sides of the wormhole debate continue to receive serious scientific attention. Theoretical physics, unlike experimental fields requiring expensive telescopes or particle accelerators, can be pursued with comparatively modest funding, primarily supporting researchers' salaries and computational resources rather than large-scale physical infrastructure, meaning a wider range of theoretical possibilities can be explored on paper even when the technology to test them observationally remains years or decades away. This relatively low barrier to entry means theoretical wormhole research continues at a steady pace, producing a continuous stream of new papers exploring various angles of the problem, even during long periods when no new observational data becomes available to test any of the resulting predictions. A pattern that can sometimes create a public impression of more active, rapid progress than the underlying observational evidence actually supports. At the same time, researchers publishing in reputable, peer-reviewed journals face strong professional incentives to remain appropriately cautious and rigorous in how they frame their conclusions, since overstating the significance of a purely theoretical result risks damaging their scientific credibility within a community that values careful, well-supported claims over exciting but poorly substantiated speculation. Let's consider, finally, how this entire field might realistically develop over the coming 10 to 20 years, based on the specific observational and theoretical avenues discussed throughout tonight's exploration. Gravitational wave detectors will very likely continue improving in sensitivity, adding progressively more merger events to the growing catalogue available for echo signal analysis, either eventually detecting a genuine, statistically robust echo signature, or continuing to push the upper limit on any such signal's possible strength closer and closer to zero, gradually ruling out an increasing range of theoretical wormhole and exotic compact object models. The Event Horizon Telescope Network, along with any successfully funded and launched space-based expansions, will likely continue producing increasingly detailed images of black hole shadows and photon rings, potentially reaching, within this time frame, the level of precision theoretically required to detect the subtle distinguishing features some models predict for wormhole mouths, though this remains dependent on securing sufficient funding and successfully overcoming significant remaining engineering challenges. Theoretical research will almost certainly continue refining the mathematical models on both sides of this question. Both those supporting the plausibility of stable, potentially observable wormholes under increasingly specific and constrained conditions, and those continuing to identify additional theoretical obstacles that make their natural or artificial existence seem even less likely than currently understood. Let's think about what the most probable outcome actually looks like, based on the current trajectory of this research, rather than either the most exciting or the most dismissive possible conclusion. Given the extraordinarily demanding theoretical requirements involved, particularly the need for exotic negative energy density in quantities vastly exceeding anything ever observed or plausibly producible using any currently known physical process, most physicists working directly in this field consider it significantly more likely that ongoing research will continue to narrow and constrain wormhole possibilities rather than eventually confirming their existence outright. This does not mean the question is scientifically uninteresting or not worth pursuing. Rigorously ruling out an exotic theoretical possibility through careful, sustained observational and theoretical effort represents genuine, valuable scientific progress in its own right, sharpening our understanding of exactly what general relativity does and does not permit under realistic physical conditions, even when the ultimate conclusion turns out to be that a particular exciting possibility, however mathematically elegant, does not actually correspond to anything occurring in the real physical universe. Let's close by returning to the broader significance of this entire line of inquiry, regardless of how it ultimately resolves in the coming decades. The fact that Einstein's century-old equations continue to generate genuinely open, actively researched questions. Questions serious scientists are still working to answer using increasingly sophisticated instruments and increasingly refined mathematical models, speaks to the extraordinary depth and lasting power of general relativity as a scientific theory. Few theories in the entire history of science have proven this durable, continuing to generate new, testable predictions and new avenues of serious research more than 100 years after their original publication, a testament to just how deeply and accurately Einstein managed to capture the true underlying structure of gravity, space, and time itself. Whether or not a real, physical wormhole is ever confirmed to exist, the search itself continues to push astronomers and physicists toward increasingly precise, increasingly creative methods of observing and understanding the most extreme objects and environments our universe contains. Extending human knowledge steadily outward, one carefully tested hypothesis at a time. Let's take a step back and think about black holes more broadly, since a deeper understanding of ordinary black hole behavior actually strengthens the case for exactly how demanding the wormhole alternative really is. Black holes come in a range of sizes, from stellar mass black holes formed by the collapse of massive dying stars, typically a few times to a few dozen times the mass of our Sun, up through supermassive black holes found at the centers of most large galaxies, some containing the mass of several billion suns, compressed into a region smaller than our solar system. Despite this enormous range in size, every confirmed black hole observed so far, whether through gravitational wave detections of stellar mass mergers or direct imaging of supermassive galactic centers, has behaved in a manner fully consistent with standard general relativity, showing no confirmed deviation of the kind a wormhole or other exotic compact object would be expected to produce. This consistency across an enormous range of masses and environments represents strong, if indirect, supporting evidence for the standard black hole model, since any viable alternative theory, including wormhole-based models, must not only explain any specific unusual observation it is invoked to address, but must also remain fully consistent with the overwhelming body of existing data that already matches standard predictions extremely well across dozens of independently observed objects. Let's think about how scientists actually go about testing a new theoretical model against this large existing body of evidence, since this process is central to how any wormhole hypothesis would eventually need to be evaluated. Whenever a researcher proposes a new theoretical model, whether involving wormholes, fuzzballs, gravastars, or any other exotic alternative to a standard black hole, that model must be checked not just against the single unusual observation that may have originally motivated it, but against the entire existing catalogue of black hole observations, including gravitational wave signals from dozens of confirmed mergers, direct imaging from the Event Horizon Telescope, and decades of indirect observational evidence from X-ray binaries and galactic center dynamics. A model that successfully explains one unusual data point while failing to remain consistent with this much larger body of existing evidence is generally considered scientifically weak, regardless of how elegant or mathematically interesting it might be in isolation, since a truly successful alternative theory needs to explain everything the standard model already explains well, while additionally accounting for whatever new or unusual observation motivated the alternative proposal in the first place. This is an extremely high bar to clear, and it is precisely why standard black hole theory, despite still containing genuine unresolved theoretical puzzles like the information paradox and the nature of the central singularity, remains the overwhelmingly favored explanation for the vast majority of astronomical objects currently classified as black holes, with wormhole and other exotic alternatives remaining confined to a small number of specific, still contested edge cases where the standard model's predictions have not yet been tested with sufficient precision to rule out every alternative possibility. Let's think about the specific role that skepticism plays within the professional physics community, since this often gets lost in more sensationalized popular coverage of exotic theoretical physics. Peer review, the process by which scientific papers are evaluated by other experts before publication, is specifically designed to catch overstated claims, insufficient evidence, or alternative explanations the original researchers may not have adequately considered, acting as a built-in mechanism of professional skepticism that every serious scientific claim about potential wormhole evidence must pass through before it can be taken seriously by the broader community. This does not mean peer review is perfect or infallible. Papers occasionally pass through this process containing claims that are later found, through subsequent independent analysis, to be less well supported than initially presented, exactly as happened with several of the early, tentative gravitational wave echo claims discussed earlier in tonight's exploration. But the overall system, imperfect as it is, generally functions as intended over time, with initially exciting but ultimately unsupported claims gradually being filtered out through repeated independent scrutiny, while genuinely robust findings tend to survive and strengthen as additional data and independent analysis continue to support them. Let's consider how this same pattern of initial excitement, followed by more careful scrutiny, has played out repeatedly throughout the broader history of astrophysics, beyond just the specific question of wormholes. When pulsars, rapidly rotating neutron stars emitting regular pulses of radio waves, were first discovered in 1967, the extremely regular, precise timing of their signals briefly led some researchers to only half-jokingly consider whether they might be detecting deliberate signals from an extraterrestrial civilization, before more careful analysis confirmed they were a previously unknown, but entirely natural, astrophysical phenomenon. Similarly, when astronomers first detected unusual dimming patterns in the light from a star known as KIC 8462852, sometimes nicknamed Tabby's star, speculation briefly included the possibility of an artificial megastructure built by an advanced alien civilization, before subsequent, more detailed observations found the dimming was very likely caused by orbiting clouds of dust, a far more mundane, but still scientifically interesting, natural explanation. In both cases, and in countless others throughout the history of astronomy, the initial exotic hypothesis generated significant public excitement and media attention, while the scientific community continued patiently gathering additional evidence until a more conventional, but ultimately correct, explanation could be confirmed with confidence. The ongoing wormhole search follows this exact same well-established pattern, an exciting, exotic possibility, generating understandable public fascination, being carefully and patiently tested against a much more mundane, but currently far better supported, conventional explanation. Let's think about what makes the wormhole case somewhat different from these previous examples, since it is worth acknowledging this distinction honestly. Unlike pulsars or Tabby's star, where the conventional explanation was eventually confirmed with a high degree of certainty, the wormhole question remains genuinely open in a way these other historical examples do not. Precisely because the theoretical framework predicting potential wormhole signatures, gravitational wave echoes and photon ring distortions, remains scientifically legitimate and not yet definitively ruled out by current observational precision. This means tonight's exploration cannot offer the same kind of satisfying resolution that stories about pulsars or Tabby's star eventually reached, where an initial mystery was clearly and definitively solved. Instead, the honest scientific conclusion remains genuinely unresolved. A real, still open question, actively being investigated using the best tools currently available, with a final answer likely still years, or even decades, away, depending on how quickly relevant observational technology continues to improve. Let's think about why this kind of genuine, unresolved uncertainty is actually valuable, rather than simply frustrating, from a broader scientific perspective. Science does not always provide neat, immediate answers, particularly when investigating phenomena at the absolute extreme edge of what current technology can observe or measure with sufficient precision. The wormhole question represents exactly this kind of genuine frontier, a place where our best current theories provide a mathematically consistent, testable prediction, but where our best current instruments have not yet reached the sensitivity required to definitively confirm or rule out that prediction, leaving space for continued honest scientific uncertainty rather than a premature, falsely confident conclusion in either direction. Let's think finally about how this kind of patient, uncertain, ongoing scientific process connects to the broader themes explored throughout this channel's other episodes, since it reflects something true about nearly every frontier of modern astronomy and physics. Whether discussing the far side of the moon, the buried ocean beneath Pluto's icy crust, or the theoretical possibility of a traversable wormhole, the same basic pattern repeats again and again throughout modern science. Careful theoretical prediction, followed by painstaking observational effort, followed by years or decades of patient refinement, gradually narrowing the range of remaining uncertainty until either confirmation or exclusion finally becomes possible. This is simply how genuine scientific knowledge advances at the true frontier of human understanding, slowly, carefully, and honestly, resisting the temptation toward premature certainty in either direction, until the evidence itself becomes strong enough to finally settle the question one way or the other. Let's think once more about Kip Thorne specifically, since his career offers a useful window into how a serious physicist navigates the boundary between rigorous science and popular fascination with exotic concepts like wormholes. Thorne spent decades working on the mathematics of general relativity, contributing significantly to gravitational wave theory long before LIGO's eventual construction, work that would later earn him a share of the Nobel Prize in Physics in 2017 following LIGO's historic first detection. His involvement in wormhole physics began, as mentioned earlier, almost as a favor, helping a science fiction author ensure a novel remained scientifically plausible. Yet this seemingly casual starting point led to genuinely serious, rigorously published scientific work that continues to shape how physicists think about exotic matter and traversable wormholes even today. Decades later, Thorne served as a scientific consultant on the film Interstellar, helping ensure its own depiction of a wormhole, used as a plot device, allowing characters to travel to a distant galaxy, remained as scientifically grounded as possible, within the constraints of a mainstream Hollywood film, resulting in visual depictions of gravitational lensing and black hole accretion disks, detailed and accurate enough that Thorne and his collaborators published actual scientific papers based on the visualization techniques developed for the movie. Let's think about what this particular career trajectory suggests about the relationship between rigorous science and popular imagination when it comes to concepts like wormholes. Thorne's example demonstrates that serious, technically rigorous scientific work and broader public fascination with exotic concepts are not mutually exclusive and can, in the right circumstances, productively reinforce each other, with popular interest in dramatic concepts like wormholes occasionally motivating genuinely valuable scientific investigation. While that same scientific rigor, in turn, helps ensure popular depictions remain grounded in real, defensible physics, rather than pure fantasy. This channel's own approach to tonight's topic has tried to follow a similar spirit, taking a concept with enormous popular and cultural fascination and grounding it as carefully and honestly as possible in the actual, current state of serious scientific research. Neither dismissing the topic as pure fantasy, unworthy of discussion, nor exaggerating its current level of observational support beyond what the evidence actually shows. Let's think about the specific technical challenges facing the next generation of gravitational wave detectors, since these challenges directly determine how quickly the echo signal question might eventually be resolved. Ground-based detectors like LIGO and Virgo face fundamental sensitivity limitations imposed by seismic noise, the constant, faint vibrations of the Earth itself, which become increasingly difficult to filter out at the very low frequencies where certain predicted echo signals would be expected to appear most clearly. This is part of why space-based detectors like the planned LISA mission are considered so valuable, since operating in space entirely removes the problem of seismic noise, allowing sensitivity to a completely different, generally lower range of gravitational wave frequencies than any ground-based detector could ever achieve. Frequencies particularly relevant to mergers involving much more massive, supermassive black holes rather than the smaller stellar mass black holes LIGO and Virgo primarily detect. Bridging the gap between these two detector types, current ground-based instruments and future space-based instruments involves an intermediate range of frequencies that neither type of detector is optimally suited to observe, a gap some proposed future missions, involving intermediate scale detectors either on the ground or in space, aim specifically to address, though none of these intermediate proposals currently have confirmed funding or a firm launch timeline. Let's think about international collaboration in this field, since gravitational wave astronomy, perhaps more than almost any other area of modern physics, depends heavily on coordinated effort across many different countries and research institutions. LIGO itself operates as a collaboration between multiple observatories within the United States, working closely with the European Virgo detector and Japan's Kagra detector, with all three facilities sharing data and coordinating observation schedules to maximize the ability to precisely locate the source of any detected gravitational wave signal in the sky, since a signal detected by only a single observatory provides much less precise directional information than the same signal detected simultaneously by multiple, geographically separated instruments. This kind of large-scale, multinational collaboration reflects a broader pattern common throughout modern astrophysics, where the scale, cost, and technical complexity involved in building and operating cutting-edge scientific instruments increasingly requires pooling resources and expertise across many countries, rather than any single nation attempting to pursue this kind of ambitious, expensive research entirely independently. Any future breakthrough in the search for gravitational wave echoes, or any other potential wormhole signature, will very likely emerge from exactly this kind of broad, carefully coordinated international scientific effort, rather than from any single research group or institution working in isolation. Let's think about how ordinary people, without specialized training in theoretical physics, can meaningfully engage with this kind of ongoing scientific question. beyond simply consuming popular science content like tonight's exploration. Several gravitational wave observatories and research collaborations maintain publicly accessible data archives, allowing anyone with sufficient technical background and interest to download and analyze real gravitational wave detection data themselves, an unusually direct and transparent level of public access compared to many other areas of cutting-edge scientific research. Citizen science projects in various areas of astronomy have also occasionally contributed meaningfully to broader research efforts, with volunteers helping classify astronomical images or search through large datasets for unusual patterns that automated analysis methods might miss. Though no major citizen science initiative currently exists specifically focused on the gravitational wave echo, search discussed throughout tonight's episode. For most people, meaningfully engaging with this kind of research means simply staying informed about ongoing developments, understanding enough about the underlying physics to critically evaluate news coverage when new claims inevitably emerge, and maintaining the kind of patient, evidence-based curiosity that mirrors the same careful, methodical approach the scientists themselves bring to this genuinely open and fascinating question. Let's think about the mathematics of space-time curvature a little more carefully, since a slightly deeper understanding helps clarify exactly why physicists describe wormholes as mathematically permitted but physically demanding, rather than simply impossible outright. Einstein's field equations relate the curvature of space-time directly to the distribution of mass and energy present within it, meaning that, in principle, any mathematically describable distribution of mass and energy corresponds to some specific, well-defined curvature of space-time, including, as Einstein and Rosen discovered, curvatures that produce bridge-like or tunnel-like structures connecting otherwise separate regions. The equations themselves do not distinguish between mass and energy distributions that occur naturally, such as the collapse of a massive star, and those that would require deliberately engineered exotic conditions never observed occurring naturally anywhere in the universe, meaning the mathematics alone cannot tell us whether a particular solution, however elegant, actually corresponds to something the real universe could ever produce or sustain. This is precisely the gap between mathematical possibility and physical plausibility that defines the entire wormhole debate, a solution that Einstein's own equations permit, sitting uneasily alongside the separate, equally important question of whether the specific exotic conditions required to realize that solution could ever actually occur, whether through natural processes or deliberate future engineering by an advanced civilization. Let's think about how this same tension between mathematical possibility and physical plausibility appears elsewhere in physics, beyond just the specific case of wormholes, since recognizing this broader pattern helps put the wormhole question into useful context. Negative mass, a hypothetical form of matter that would respond to gravity in the opposite direction from ordinary matter, appears as a mathematically consistent possibility within certain theoretical frameworks. Yet no confirmed example of negative mass has ever been observed anywhere in nature, despite decades of careful theoretical and experimental investigation. Tachyons, hypothetical particles that would travel faster than the speed of light, similarly emerge as a mathematically consistent solution within certain versions of relativistic physics. Yet extensive experimental searches have found no confirmed evidence that any such particle actually exists, and most physicists consider their existence, based on current evidence, to be highly unlikely if not effectively ruled out entirely. Wormholes fit into this same broader category of mathematically permitted, but observationally unconfirmed, exotic physics, standing alongside negative mass and tachyons as concepts that emerge legitimately from our best theoretical frameworks, while remaining, so far, entirely unsupported by any direct experimental or observational evidence confirming their actual existence in the real, physical universe. Let's think about why physicists continue to take these kinds of unconfirmed, exotic possibilities seriously, rather than simply dismissing them once initial searches fail to find supporting evidence. Part of the answer lies in the historical track record of theoretical physics. where several concepts initially considered purely mathematical curiosities, including black holes themselves, antimatter, and gravitational waves, were eventually confirmed observationally, sometimes decades after they were first proposed theoretically. Only after observational technology finally advanced enough to detect the subtle signatures these theories predicted. Antimatter, for example, was first proposed theoretically by physicist Paul Dirac in 1928, based purely on the mathematical requirements of combining quantum mechanics with special relativity, and was experimentally confirmed only a few years later, in 1932, when the positron, antimatter's electron counterpart, was actually detected in cosmic ray experiments. Gravitational waves themselves, predicted directly by Einstein's general relativity in 1916, were not directly detected until nearly a full century later, in 2015, illustrating just how long a genuinely correct theoretical prediction can sometimes wait before observational technology finally becomes sophisticated enough to confirm it decisively. Let's think about what these historical precedents suggest, and equally importantly, what they do not suggest, about the current status of wormhole physics. These examples demonstrate that a long delay between theoretical prediction and observational confirmation does not automatically mean a theoretical prediction is incorrect, providing a legitimate historical basis for physicists to continue taking exotic, currently unconfirmed predictions like wormholes seriously, rather than assuming that decades without confirmation necessarily means the underlying theory must be wrong. At the same time, these same historical examples do not provide any guarantee that wormholes will eventually be confirmed simply because other exotic theoretical predictions eventually were. Antimatter and gravitational waves were both confirmed because they made specific, precise, testable predictions that observational technology eventually became sophisticated enough to check directly. And both concepts, importantly, did not require anything resembling wormholes' extraordinarily demanding, exotic negative energy requirements, a key difference that continues to make many physicists considerably more cautious about wormholes' eventual prospects compared to these other historical examples of successfully confirmed exotic physics. Let's think about this distinction a little more carefully, since it represents one of the most important nuances in fairly evaluating the current state of wormhole research. Antimatter's theoretical prediction followed directly and unavoidably from combining two already well-established theories, quantum mechanics and special relativity, meaning its existence was, in a real sense, already implied by physics that had already been extensively tested and confirmed in other contexts, well before antimatter itself was directly observed. Wormholes, by contrast, while mathematically consistent with general relativity, require additionally postulating the existence of exotic negative energy density in quantities that have never been observed occurring naturally anywhere, and that remain, even in laboratory conditions like the Casimir effect, many orders of magnitude smaller than what would actually be required, representing a considerably larger, more speculative theoretical leap than was ultimately required to correctly predict antimatter or gravitational waves. This is not a claim that wormholes are definitely impossible, since physics has been surprised before, and genuine scientific humility requires acknowledging the limits of current understanding rather than declaring any mathematically consistent possibility permanently closed. It is, however, a fair and important explanation for why most physicists working in this field remain considerably more skeptical about wormholes' eventual confirmation than they were, in hindsight, about antimatter or gravitational waves, given the significantly larger and more speculative theoretical gap that would need to be bridged by future discoveries. Let's think once more about the numbers involved in the negative energy problem, because putting a rough scale on the requirement helps make the difficulty easier to genuinely appreciate. Some calculations, based on the Thorne-Morris model and similar traversable wormhole proposals, suggest that holding open a wormhole even a single meter across would require a quantity of negative energy comparable in magnitude to the total positive energy contained within an entire star, concentrated into an impossibly thin, precisely arranged shell surrounding the wormhole's throat. The largest quantities of negative energy density ever measured in a laboratory, produced through the Casimir effect using the most sensitive experimental setups currently available, remain smaller than this requirement by a factor difficult to even meaningfully express in ordinary language, some estimates placing the gap at many tens of orders of magnitude. A difference so vast that closing it would likely require not just incremental technological improvement, but an entirely new, currently unknown physical principle or process. This is the specific, concrete reason most physicists describe traversable wormholes as technically permitted by the mathematics, while remaining practically almost inconceivable given anything resembling current or foreseeable technology. A distinction that matters enormously when evaluating any specific claim suggesting scientists may have found evidence of one. Let's think, one final time, about how this specific numerical gap shapes realistic expectations for what future research might actually achieve, as opposed to what remains confined to the realm of speculative fiction. Closing even a small fraction of this enormous gap through some currently unforeseen theoretical breakthrough in quantum field theory or a deeper understanding of the vacuum's true structure would itself represent one of the most significant discoveries in the history of physics, regardless of whether it ultimately led to an actual, functioning wormhole. This is part of why continued research into the fundamental nature of the quantum vacuum, negative energy, and the deep, still unresolved relationship between quantum mechanics and gravity remains scientifically valuable in its own right, independent of whether it ever specifically produces a workable wormhole, since the underlying physics being investigated touches on some of the most fundamental, unresolved questions about the basic structure of reality itself. Let's think, before closing, about a handful of specific candidate objects that have appeared repeatedly in both scientific literature and popular discussion as potential, if still unconfirmed, wormhole candidates, since naming them directly helps ground tonight's discussion in real, ongoing research rather than pure abstraction. Sagittarius A star, our own galaxy's central supermassive black hole, remains the single most intensively studied candidate for any future distinguishing observation, given its relative proximity and the existing, continuously improving Event Horizon Telescope imagery already available for direct comparison against theoretical predictions. The black hole at the center of the galaxy M87, the first object ever directly imaged by the Event Horizon Telescope in 2019, continues to serve as a second, independent test case. Its significantly larger mass and different surrounding environment, providing a useful point of comparison against Sagittarius A star, helping researchers distinguish genuine wormhole-specific signatures from effects that might simply depend on an individual object's particular mass or environment. Several confirmed gravitational wave merger events, catalogued by LIGO and Virgo since 2015, continue to be revisited and reanalyzed as detector sensitivity improves and analysis techniques become more sophisticated, with researchers periodically re-examining the same historical data using newer, more refined statistical methods specifically designed to detect increasingly subtle potential echo signals that earlier, less sophisticated analysis techniques might have missed entirely. Let's think about how this kind of repeated reanalysis of existing data connects to the broader pattern of careful, incremental scientific progress discussed throughout tonight's episode. Unlike a single, one-time observation that either confirms or fails to confirm a specific hypothesis, gravitational wave data, once collected, remains permanently available for future reanalysis using whatever improved statistical and computational techniques researchers develop in subsequent years. Meaning today's null result does not necessarily represent a final permanent answer, but rather the current best conclusion available given today's analytical tools. This is part of why physicists remain reluctant to declare the wormhole echo question definitively settled in either direction. since future reanalysis of existing data, combined with the ongoing addition of new merger events, continues to offer a realistic path toward either eventual confirmation or increasingly strict exclusion, without requiring any fundamentally new observational technology beyond what already exists today. Let's think, too, about how this same pattern of continuous reanalysis applies to the broader astronomical archive beyond just gravitational wave data specifically. Historical astronomical images, some captured decades ago using now outdated technology, are regularly reprocessed using modern computational techniques, occasionally revealing subtle details or patterns that the original researchers, working with the analytical tools available at the time, simply could not have detected. A pattern discussed earlier in this channel's exploration of Pluto, where New Horizons data continues yielding new insights nearly a decade after the original flyby. The search for wormhole evidence benefits from this same broader pattern, meaning that even without any new telescope or detector coming online, continued improvement in data analysis techniques alone provides a genuine, ongoing avenue for potential progress, squeezing additional insight out of data that has, in some cases, already existed for years, waiting for sufficiently refined analytical methods to finally reveal whatever subtle patterns it might or might not actually contain. Let's think about the broader lesson tonight's story offers about the nature of scientific patience, since it extends well beyond this single, specific question about wormholes. Nearly every genuinely difficult scientific question follows a similar arc, an idea emerging from careful mathematical reasoning, decades of gradual refinement as new tools and new generations of researchers revisit old assumptions, and, eventually, either confirmation or exclusion, arriving only once observational technology finally catches up to what the theory originally predicted. Black holes themselves followed this exact pattern, first appearing as a strange mathematical solution to Einstein's equations. Dismissed by many physicists, including Einstein himself, as too exotic to correspond to anything physically real. Before decades of careful theoretical and observational work eventually confirmed not only their existence, but their surprising prevalence throughout the universe, from stellar remnants to the supermassive anchors sitting at the center of nearly every large galaxy. Wormholes may yet follow a similar path toward eventual confirmation. Or they may instead join the growing list of mathematically elegant possibilities that, upon sufficiently careful investigation, are ultimately found to have no genuine counterpart anywhere in the physical universe. Either outcome represents genuine scientific progress, and either outcome is still, as of tonight, entirely possible, waiting on exactly the kind of careful, patient, methodical work already described throughout this episode. Let's think, one more time, about what makes this particular scientific frontier so uniquely compelling compared to many other open questions in modern physics. Most unresolved questions in physics involve phenomena so remote from ordinary human experience, so deeply embedded in abstract mathematics, that connecting them to any intuitive, easily graspable concept proves genuinely difficult. Wormholes occupy an unusual middle ground, emerging from exactly this same rigorous, abstract mathematical framework, yet connecting directly to one of the most universally appealing ideas in all of human storytelling: a shortcut, a hidden passage, a tunnel connecting two distant places that would otherwise remain forever separated by impossible distance. This rare combination, serious, rigorous science, paired with an almost universally intuitive underlying concept, helps explain why this particular question continues to capture public imagination so persistently, decade after decade, long after many other equally significant but less intuitively graspable areas of physics have faded from broader public awareness. Let's think, finally, about what continuing to watch this space might actually look like for anyone curious enough to follow along in the coming years. Major gravitational wave detection announcements typically receive significant media coverage, offering a natural, easily accessible point to check in on whether any new merger event has produced evidence relevant to the ongoing echo search, discussed throughout tonight's episode. Announcements from the Event Horizon Telescope collaboration, including any future high-resolution imaging results from Sagittarius A star or other targets, similarly tend to receive widespread attention, offering another natural checkpoint for anyone interested in tracking whether photon ring observations have advanced closely enough to the theoretical threshold required to distinguish a wormhole from an ordinary black hole. Beyond these major announcements, the steady, less publicly visible accumulation of additional data and increasingly refined analysis continues quietly in the background, exactly the kind of patient, incremental progress that defines most of modern astrophysics, whether or not it happens to produce a dramatic, headline-generating result in any particular year. Let's take one more slow pass through the full arc of tonight's exploration, gathering the threads together before we finally close. Einstein and Rosen found a bridge hiding inside the mathematics of general relativity in 1935. A strange, almost accidental discovery buried within equations originally written to describe something else entirely. Wheeler showed decades later that this bridge, in its simplest form, would collapse in an instant, seemingly closing the question before it had truly begun. Thorne and Morris reopened it in the 1980s, showing that exotic matter with negative energy density, a genuinely strange but experimentally confirmed property of the quantum vacuum, could in principle hold such a bridge open, if only enough of it could ever be gathered or produced. Maldacena and Susskind connected the idea to quantum entanglement decades further on, suggesting that wormholes, in some deep and still poorly understood sense, might already be woven invisibly throughout the universe at the smallest possible scales. And now, gravitational wave detectors and global telescope networks, tools that did not exist in any usable form even 20 years ago, are finally sensitive enough to begin searching for real, physical evidence, one merger at a time, one image at a time, one carefully reanalyzed dataset at a time. Let's think about how far this places us from the century that started it all, and how far we still likely have left to go. 90 years separate Einstein and Rosen's original discovery from tonight. Fewer than 10 years separate us from the first gravitational wave detection ever recorded, and fewer still from the first direct image of a black hole's shadow. Whatever answer eventually emerges, whether confirmation, exclusion, or some outcome not yet imagined by anyone currently working on this problem, will likely arrive within a time frame far shorter than the 90 years already spent getting the question to where it stands today. A reflection of just how rapidly observational technology in this field continues to accelerate. Let's think one more time about the sheer number of independent research threads that would all need to converge before anyone could responsibly declare this question settled. Gravitational wave echo analysis, photon ring imaging, laboratory measurements of negative energy density, and theoretical modeling of exotic matter requirements all represent separate, largely independent lines of investigation, each pursued by different research groups, using different instruments, different mathematical techniques, and different underlying assumptions about what a genuine wormhole signature would actually look like. A confirmed discovery would likely require agreement across several of these independent threads simultaneously, not a single isolated result from just one method, since the history of physics has repeatedly shown that isolated, unreplicated findings, however exciting at first, frequently fail to hold up once other independent groups attempt to verify them using different approaches. This requirement for convergent, independently replicated evidence is not bureaucratic caution for its own sake. It reflects a hard-earned lesson from decades of experience that the universe's most extreme and unusual claims deserve the most rigorous, multiply-confirmed scrutiny before being accepted as genuine scientific fact, rather than remaining, as wormholes currently do, a fascinating, still open, and genuinely unresolved question at the very edge of what modern physics can currently investigate. Let's think about how today's null results actually strengthen, rather than weaken, our overall confidence in general relativity itself, regardless of how the wormhole question specifically resolves. Every gravitational wave signal recorded so far has matched standard black hole merger predictions with remarkable precision. Every black hole shadow imaged so far has matched the expected photon ring pattern almost exactly, and every laboratory test of general relativity conducted over the past century, from the bending of starlight during solar eclipses to the precise timing of orbiting pulsars, has continued to confirm Einstein's original equations with extraordinary accuracy. The wormhole search, in this sense, represents scientists testing the absolute outer limits of an already extraordinarily well-confirmed theory, probing whether some of its more exotic mathematical solutions correspond to anything physically real, rather than questioning the theory's fundamental validity, which remains about as solidly established as any theory in the entire history of physics. Let's think, briefly, about how this specific channel's own approach to space and physics topics tries to mirror the same careful standards used throughout genuine scientific research. Every claim discussed tonight has been presented alongside its actual current level of scientific support, distinguishing clearly between mathematically consistent possibilities, laboratory-confirmed phenomena, and claims that remain genuinely unconfirmed despite ongoing, serious investigation. This approach means some questions, including tonight's central question about whether a real wormhole has finally been found, simply cannot be answered with a satisfying, definitive yes or no. Since the honest, current state of the science itself does not yet support such a clean resolution. Recognizing and sitting comfortably with that kind of open, unresolved uncertainty is, in its own way, one of the most valuable habits of mind that engaging seriously with real science can offer. A willingness to hold a fascinating question open, patiently, for as long as the actual evidence requires, rather than reaching prematurely for a satisfying but unsupported conclusion in either direction. Let's close tonight's exploration by returning to the original question one final time, now with a fuller understanding of everything involved in actually answering it. Have we finally found a real wormhole? The mathematics permitting such a structure has existed since 1935. The theoretical framework describing how one might, in principle, remain stable enough to traverse has existed since the late 1980s. The observational tools potentially capable of detecting subtle evidence for or against their existence, gravitational wave detectors and increasingly powerful telescope arrays, have only existed in their current, sufficiently sensitive form for less than a decade. Given this timeline, it should come as no surprise that a definitive answer does not yet exist. Every gravitational wave echo search conducted so far has returned inconclusive or negative results. Every photon ring image captured so far remains consistent with an ordinary black hole. Every laboratory measurement of negative energy density remains many orders of magnitude too small to support even a microscopic traversable wormhole, let alone one large enough for anything meaningful to pass through. And yet, the search continues, driven by the same careful, patient scientific curiosity that has, throughout history, occasionally transformed the strangest, most mathematically abstract predictions into confirmed physical reality, given enough time, enough patience, and enough steady improvement in the tools available to actually look. For now, the honest answer remains exactly what it has been throughout tonight's exploration. Not yet. But for the first time since Einstein and Rosen first noticed a strange bridge hiding inside their own equations nearly a century ago, the question of whether that bridge actually exists anywhere in the real universe has finally become something scientists can meaningfully investigate rather than simply imagine.